Setting up of governing equations in problem formulation. This video is part of a course on food physics, of which this is the modeling section. Now, this is the fourth one, even though it says 3, it is the fourth one because there's an introductory one and then there is a summary one. Fourth one of 7 videos in a series on problem formulation. So this particular one is about deciding on the governing equations. Now, of course, we're not going to derive all of the governing equations. That will take forever. And we have separate theory section where we do have many of these derivations, and we would refer you to those videos. Here we are going to talk about the logic behind picking the most appropriate equations. Now, as you watch these, when suggested, you can stop and apply the principles to your own model or your own project before moving on to the next step. We can divide this logic of deciding on the governing equations into 3 parts. What physics is involved, and in that physics, what are the general governing equations, and then for each equation, what are some of the relevant terms, what are some of the details that we need to keep. So we can divide it into 3 parts. Let's look at the first one. So of course there's no one way to approach such a problem, and here is just one approach to try to decide on those governing equations and what physics are involved. How do we do that? So to get started is not always easy, but we do have a few things that we can look into at this stage. First is, if this is a modeling project, then we should definitely look for what previous models have already been published. That is absolutely the starting point. Next, we can look at even qualitative literature. So if we're doing a baking modeling, lots and lots of books are there, food science books, even cooking books, that would give us some ideas of what this baking process is like. Next, we look for very general understanding of it, just based on, not even scientific or technical literature, but just general understanding of the process based on just our everyday experiences or just what people think about it. We put all this together, and finally a very powerful thing to do at this stage is to do a quick experiment to have a overall understanding of this process, a simple understanding of the process before we get started. Now, we fully intend it to be revised with time as we learn more from the model and from additional experiments, and especially when we're comparing the experimental results with the modeling output, that's the model simulations, in the validation process. So it's going to get revised, but we have to start somewhere, and here is one approach that should work in general to get started. Once we have at least a qualitative picture of the physics, I mean, we could have better than qualitative picture, we could have previous models that are very close to what we need, but we may not be so lucky. But we need at least a qualitative picture. I need you to see that modeling cannot invent the physics. We have to know the physics to start with, and then we get into modeling. Modeling can give us some of the details that we cannot see, but it cannot come up with the overall physics. So in this stage, to decide on which equations, we're going to look into what's called the general frameworks for modeling. Now, our context here is mechanistic modeling, as distinct from machine learning or other ways of empirically modeling. Those are also models, but we are interested in mechanistic modeling. So mechanistic modeling is based on fundamental principles which are stated as equations. Because processes have things in common, let's say baking and drying and frying and microwave reheating, they all have some things in common. This kind of mechanistic modeling always start from similar set of equations. If we want to build a model for drying, we could actually start from equations that are maybe developed for baking, but we may have to change it some. So similar sets of equations or similar physics that cover many different processes can be called a modeling framework. So this same set of equations that you see here, we can call this as a framework. There are many such frameworks. So here is an overview of many of the common general frameworks. Each one of these frameworks is discussed in detail in the theory section of this course. So in the theory section, there is actually a video for each one of these rectangles that you see here. The frameworks, there's a lot on this slide, so let me go slow. The frameworks go from the simplest, like a lumped parameter, to maybe more involved, like a single or multi-phase but distributed model, all the way to multi-phase porous media with phase change and deformation, like that would be needed for a bread baking. So which one of these frameworks do we choose? This is not very obvious at all, and we should consider a number of factors. So let's look at those factors. So how mechanistic do we want to be? Let's take the example of a frying process and models for frying process. So frying has been modeled as a completely lumped parameter model where heat and moisture transfer is considered lumped, meaning just one temperature and one moisture content as an average moisture content. Then it has also been modeled as a two-region, or what's called a sharp boundary model with core and crust, and evaporation is happening only at the interface with separate equations for the core region and crust region. So this has been done. Also, frying has been modeled with evaporation everywhere, distributed all throughout, and also considering some other details in here. All these models, I did not cook them up. they exist in the literature. So they obviously have served some purpose. So the question is, which one do I choose? Which way do I go? This depends on my goal. If my goal is a quick understanding, quick relationship between, let's say, temperature and time, or moisture and time, and my product is not going to change that much, and I have no need for mechanistic understanding, then all I need is this lumped parameter model. Whereas if I want to know more details of the frying process, then we need the more comprehensive model. So in this continuum, from very empirical to very mechanistic modeling approach, we try to make the models the most mechanistic possible. Why? One is that would give us the most predictability as the product or process changes, and also we understand the physics the best possible way. Now, with more mechanistic model, it's not free. As they say, no such thing as a free lunch. And so with more mechanistic model comes more computational complexities. Now, this important quote was presented earlier. More than in any other step, this quote is critical at this step of deciding on which governing equations to use. We do not want to keep physics that make it unnecessarily complex, and neither do we want to make it too simple and throw out some important physics. Here is an example of the type of considerations that could go into choosing a framework or a set of equations. So I'm picking one example of the porous media formulation. Now, of course, I'm biased because that is the formulation that I'm most familiar with. But also I am choosing this one because it is one of the most comprehensive formulation, and you don't want to choose such comprehensive formulation lightly because it's a lot more work than choosing a simpler framework. So you have to make sure that you really need this complexity. So this formulation, this porous media formulation, is multi-component, multi-phase porous media model, and now we can discuss when it is needed and when it is not. Now we can divide a food product into two types of possibilities. Either the product stays saturated, which I'll say in a second, like meat, that stays, that is considered to stay saturated during cooking. As it loses water, it shrinks, so it can stay saturated. Or the other group of materials that is the most that are unsaturated. Now, it has been shown that the porous media based models can capture the physics of meat cooking by considering it to stay saturated. So if we have data from the past that shows that yes, having a porous media model and considering it saturated works for meat cooking, so that would be a good reason to go for this porous media model for meat. Now, when the porous media goes at least partly unsaturated, which is most of the situations, we can think of two different groups. Either in processes that have rapid gas generation, and the other group is not so rapid gas generation. So in rapid gas generation, when do we have this kind of situation? This could happen, for example, in microwave and radio frequency heating that generates a lot of internal heat and therefore uh, evaporates water, generating pressures. And so we have a pressure driven flow, and also this rapid gas generation can happen in high heat flux. For example, some infrared heating, high flux infrared heating, or puffing, or in deep frying. Another example could be presence of CO2, internal CO2 generation, as in baking process, that will also generate pressure. So all these situations where it generates pressure and there's pressure driven flow, we really have no choice but to think of this porous media formulation. Now, dropping pressure driven flow would make the model too simple, and this is an example of dropping the important physics. So dropping this one would be making simpler than it should be. On the other hand, there could be processes that the gas generation part is very slow. So this could be, for example, a slow drying process where there is not as much internal evaporation, or some storage situations where we have multi-component moisture transfer. So there, the pressure-driven flows are not as important. So the consideration of full porous media model for these problems may not be necessary, because the gas pressure driven flow is probably very little. So we just saw an example of one of the frameworks and a sort of a logical steps to try to see whether that framework is going to be needed for a particular process or not. So we can do similar things about other framework. So few more general comments on the best approach or getting the most appropriate sets of equations. It is guided by several factors. At the end of this process, we're going to get a framework, or we're going to have decided on a framework to be used. This decision is not easy and should not be taken lightly, because if we do this casually, then we are creating problems for later on. Now, there are several factors to be considered. First, keep the goal. We have to keep the goals in mind. So keeping the goal in mind, we find the simplest model in a similar or related process. If the goal is to understand more details of the physics, we choose the most complex framework. Well, if it is just to get simple overall parameters like average moisture with time, we choose a much simpler framework. Prior knowledge and group expertise are two of the most important factors. We should not get into modeling a physics based on the availability of a software. For example, we should not get into modeling microwave heating if I do not know much of electromagnetics. So the expertise to which my group or myself feel comfortable should very much be considered at this stage of choosing a framework or the complexity of a framework. We should also consider for example, the computing software and hardware that is available to us to solve the equations as we are trying to decide on which equations would be defining our model. Because if we are proposing to solve those equations, we have to make sure that those equations are indeed solvable by the software that we have access to. Finally, it is important at this stage to consider the validation aspects. All models need to be validated, so it is prudent to formulate the problem in a way that we have validation data for. So it is the model outputs, the model simulations we'd be able to compare them with the data that we have, either with measured data available in the literature or something we will collect as part of the project. This should be considered at this stage. If they are not consistent, if we have the model predicts some quantities but the validation data available is something else, then we will have to later change the model or do fresh experimentation. So the validation possibilities, how are we going to validate the model, should be considered at this stage. So with those general guidelines, once we have chosen the framework or the general approach, past modeling work and textbooks typically give us the detailed equations. So for single phase transport equations, the best source has been this book on transport phenomena by Bird Stuart Lightfoot. As most people know, this has been the single most source for single phase transport equations for over 50 years. The other one on the other end, it's sort of more closer to food, is this multi-phase, multi-component transport in porous media applied to food. And there we have summary papers from the research groups of Datta, that's the narrator, and also from Thakur. The two of us have put out this kind of summary papers of our formulations. For the porous media model from our group here, we have complete videos available of the theory as part of this series in the theory section. You can also look at summary papers from our group or from Thakur's group, as their two different porous media approaches. Here are some example governing equations for single phase transport processes. Of course, we're not here to discuss all governing equations. Here's an example of the single phase transport equations in rectangular Cartesian coordinate and in 2D in this case. If we need temperature, we need to include this equation. Remember, in this step we are now trying to decide the equations, the specific equations, and even more details later on. So if we need temperatures, we need to solve the heat equation. If we need concentration, then you need to solve the species mass balance equations. If you need flow, then you have to solve this one as well, the Navier-Stokes equations. So for details of the derivations of these equations and other coordinates and so on, all the details can be nicely seen in the book by Bird from 2006 or its later versions. Now, all the discussions so far has been for one class of physics, transport processes. To make the models more realistic, more complexities, more and various physics can be added. So, at this stage, before we get into the possibilities, it is important to note that we need to have a realistic idea of what technical expertise we have available and what sort of computing software we have available so that we can actually solve those other physics or more realistic physics. For example, coupling with other physics has been done for microwave, uh, that included many uh, researchers, including us, and then radio frequency, again, many researchers, including Mara, um, and also very active areas like high pressure and plasma. And my apologies that I do not have all the latest names of the best models or the most comprehensive models in this area. Um, but what is coupling? Coupling, in case of microwave, for example, as you heat, the material, of course, changes temperature. As it changes temperature, its dielectric properties change. So the microwave physics keeps changing with heat transfer physics. And so they are coupled together. So coupling requires other considerations. For example, is it one-way coupling? Is it just temperature affecting the electromagnetics? But is it also the electromagnetics affecting the temperature, which is the case for microwaves, that it is both ways. Electromagnetics affects the temperature and temperature affects the electromagnetics. So that's a two-way coupling. Another way to make the models more realistic is to develop conjugate models, for example. And this has been, there's quite a bit of work has been done by the Moraga group in this area. So what's a conjugate model? In general, for example, if we have a solid and fluid flowing over the solid, what we normally do is use some sort of a heat transfer or mass transfer coefficient at the boundary. But we don't have to. We can solve the equation for the solid and the equation for the fluid simultaneously. Then we don't need this H or HM, and it gives us a much more comprehensive picture, and so it's more advantageous. It gives us, how the H and HM would have varied with position and so on, but it's obviously more work. Another type of work is multi-scale models that have been pioneered by the Nicolai group. For how this is useful and to make it more realistic, when we do not have properties, we do not have transport properties, for example, then we can solve the same physics or the physics involved at a much smaller scale. So for example, in their work of storing fruits, then we can take like a millimeter cube of that fruit and solve the physics in its full details, and from there we can actually back out the effective properties which we can use at a larger scale. And so we are now able to use modeling to actually um, you know, extract properties that we need at a larger scale. So these are more advanced topics, and we're unable to go into these, for more details. One can look up the literature, as much work has been done in every one of these areas, and several researchers worldwide are active. So we should consider these complexities if it is really needed. That's the most important part in this problem formulation stage. In our quest for making models more realistic, we can develop models that can predict quantities that are more readily usable, like quality or safety, as distinct from just temperatures or moisture. Um, so we can predict these quantities. Now there are frameworks for these as well. And let's see one of those frameworks with predicting color as an example. So as part of the framework, there are three things. The first one we need is local kinetics. So that basically means in this case is what is the rate of color formation, and that rate kinetics has what kind of temperature dependency. So rate kinetics and temperature dependency would give me this local kinetics, or how color is forming locally. But that now depends on the local temperature and could be moisture. So then the next step in this framework is combining the local information with the process model of the kind we have been talking about. So that will give the local temperature or moisture. And so now if we combine these two, then we get the local color formation. And the third step is when we combine these two with some sort of averaging in this case. So it could be averaging over the surface, or some other processing with this information that gives us the final quality. So this framework that I just explained for color, it's actually more general for quality prediction, and it also is kind of very analogous in case of safety prediction. So in safety prediction, we'll have a microbiological kinetics at this stage and its temperature dependency. Let's say in a sterilization process. So inactivation of microorganism and their temperature dependency. Then we combine that with like a heat transfer model. And then instead of averaging, in case of microorganisms, we may go for wherever we have the least destruction of microorganisms. So that is my additional processing instead of averaging in case of microorganism. So that kind of a framework would be quality or safety framework. Now these frameworks have been discussed in complete details in separate videos as part of this course in the theory section, to which the listener is referred to. At this problem formulation stage, it is important to note that if we are setting up equations for color or flavor or microbiological inactivation, at this point we need to make sure that we better have the kinetic data for these changes, either color or microbiological inactivation. The rate kinetics and their temperature dependence should be available at this stage. Otherwise, we will be out of luck when we actually come to do the numerical computation. So far, we have been talking about the overall physics and the framework that gives the general sets of equations for that physics. It is now time to get into the details of these equations and which terms to keep, meaning which physics to keep more details inside these equations. Choosing a framework gives us the general set of equations. We still have to customize it for our process. And let's go through this with taking the mass transfer equation as an example. So each term in this mass transport equation is belonging to a, if we could call a sub-process or a sub-physics, and we have to question how important is that particular physics. Do we need to keep it? So let's start with that. The first one is the transient term. And do we need the transient term? For example, is the time evolution really necessary, or a steady state solution would do the job? Now this may seem like, not that important question, but it is critically important in a modeling exercise, because the transient term typically increases the computing time the most. So we have to make sure that we really need it. Moving on, the next one is the convection term, or due to flow. So if it is a fluid, then we have to ask, is there significant flow? And quite often it is significant. And so then we need to keep this term with these velocities, but then we could ask the question in our quest for simplification, how do I get this velocity? Do I need to solve for the full Navier-Stokes equations, or maybe I'm doing just pipe flow? And for pipe flow, I have an analytical solution for fully developed flow, the parabolic profile. Can I simply use the parabolic profile? This can make a huge difference in computing time. And so we need to be open to these possibilities at this problem solving stage. And we should not think that just because our software can do Navier-Stokes and get these velocities, that's the way to go right from the beginning. That's not following as simple as possible, but no simpler. Okay, so the next one is the diffusion term. So we just did this one, and the next one is the diffusion term. Diffusion term, quite often we are trying to find out how significant is the diffusion term. And the right way to do that is what we call scale analysis. That we're not getting into the details, but there is one trick that we can do, and that is the model itself can tell us whether diffusion is significant or not. So what we do is we simply run the model with and without the diffusion term to see how much of a difference it makes, and that itself gives us the idea whether we need to keep the diffusion term. So in this case, we may start with maybe without the diffusion term, and then later just add the diffusion term to see how much of a difference it made. So that was diffusion. And then finally, for the source term, which would be either the species is being degraded or some of it is being generated, if those processes are significant, we should include it. But just because the process is there doesn't mean we need to include. It may be very small in comparison. And that's what we just talked about. So what we just described using the mass transfer equation is just an example. We do exact same process going through, let's say, the heat equation or any other physics. We go through to make sure each term is really needed. So end of this process, we will have a governing equation that is specific to the physical situation that we are modeling. So now we're getting very close to the models that we would actually solve. I want to talk some more about deciding which terms to drop, because it's an eternal question and it makes a huge difference in the complexity and later solving of the model. It is an iterative process, and I already mentioned in the last slide about the first kind of iteration, that the model itself, we can keep a term or drop a term to see its effect on the final solution. But the other and more important ways for doing this is what we are going to talk. So we start based on our preliminary understanding. So it's just guess based on our insight or non-dimensionalization, which is the kind of scale analysis that we talked about. So we just start from this and do the simplest possible model first, and then build this model and validate. So compare with compare the simulation results from the model with experiment, and that gives us the feedback. The experiment gives us the feedback, and based on that we either add or delete terms as needed, or sometimes it's not just adding or deleting the entire term. It could be that we used diffusivity that's not a function of moisture content, and that's not giving good results. So we need to change to diffusivities as a variable changing with moisture content. So all of those additions, all of those details get built into the model slowly. We start from a simple one, and this is an iterative process, a very important iterative process. We never start from the most complex model just because we have a software that can do it, or I have a very fancy computer that can solve it quickly. It doesn't matter. We should always start from the simplest possible model and then build in these complexities with feedback from either experiment or the modeling results themselves. Now you may pause the video here and apply the principles that we have discussed so far to develop your own equations in their final form. So not just saying species equation, but which terms in species equation your equations after this step should have only the term that you need. So you're trying to decide which equations and which terms at this step. Again, you can pause the video and do this step. That will make it very active process. We just talked about the governing equations and how to get the specific equations for the process that we are interested in. But governing equations, to actually solve them, we also need boundary conditions. And that is the topic of the next video in this series on problem formulation.